Hello everyone and welcome. In this video we are going to discuss how to design a distributed caching service. Now before getting started with this video, I would like you to go through another video that I had created on caching and its implementations. Okay. Lot of topics that I have covered in that video. I would covering that topics in very short in this particular video. Okay. Now let's get started with it. I'll put the link to that video in the description. You can check that video out. So let's get started with this thing. So what is a caching service? To understand that, let's consider a scenario. We have a client that sends query to the app. Okay. The app goes to the database to find the result of that query. The database searches for the query results in itself, and it returns the result back to the app, and the app will return the result back to the client. Okay. Now searching in database is an expensive operation. It adds latency, and in order to deal with this we introduce a memory that is faster and that stores the query and result in the form of key value pairs. Okay. It will store the results in the form of key value pairs. Now before going to the database, the app will go to this faster memory and check if the result of that particular query is present in the cache or not. Okay. This fast memory is nothing but cache only. Okay. Now what does cache store? That really depends on what is the use case. It usually stores the frequently accessed data. So whatever query you asked frequently to the database, it will store that kind of query into itself. Okay. So this is what caching is. Now how is it implemented? We know that the cache stores values in the form of key value pairs, but how would we actually implement this? So what does key store? Key stores unique identifier to the query or the data that needs to be fetched. Okay. It stores unique identifier to the query or data that needs to be retrieved. And what would be value? The actual data. Okay. But is that enough? No. Why? Because a cache is very small memory. Okay. And when it gets full, it needs to decide what it needs to remove out of it. Okay. So for this it implements eviction policies like LRU. Okay. So it needs to decide using these policies. It decides what data or what query result it needs to remove out of the cache. But is this eviction policy implementation possible with just key value pairs? Is it possible? No, it's not. Why? Because how would we know what entry came in cache at what time? If we don't know this, we don't know what was the least recently used and what was most recently used or accessed query result from the hash table. So in order to deal with this, we also use doubly linked list. Okay. So the doubly linked list node contains the actual result to the query, and we maintain the latest nodes onto the end of the doubly linked list, and whatever was less frequently used or least recently used, that we will store onto the head. So using doubly linked list, what do we need to do with the head and tail? We can decide on the implementation if it's least frequently used, most frequently used, least recently used, most recently used. Okay. So using heads and tails we can maintain the data that is least recently used and most recently used. Now why did we use doubly linked list? It is because the time of the complexity of inserting or deleting a node from any position in doubly linked list is order of 1. Okay. Now if the doubly linked list is going to contain the actual data, what will the hash table contain then? So the hash table maintains key value pair, and the key is going to be the unique identifier to the query or the data that needs to be fetched, but the value is going to be the doubly linked list node address that contains the actual data. Okay. This also takes order of 1 lookup time. So that is how we implement doubly linked list. So whatever server is going to maintain cache, or a cache server will contain this thing. This is how it implements caching service. It uses a hash table and it uses a doubly linked list. Okay, this is how a cache is implemented in a caching server. Okay, so now let's see what would be the case in distributed scenario. If we have only one caching server and we have millions of requests coming from an app, or we have millions of instances of app that are sending requests to the cache server, then the amount of data that we are going to put onto the cache is going to be huge. Okay, so it would not be possible for a single cache server to accommodate all this data. That's why we'll need a cluster of cache servers or cache machines to store all this data. Okay, so this is what happens in a distributed scenario. Okay, if that's the case, let's discuss what are the functional requirements. What would our cache need to do for our service? Like, what will the caching service do? It should be like, we should be able to put the key value pairs onto the cache, and we should be able to get, like, we'll give the key to the cache or unique identifier to our cache, and it needs to give the result back to us. So these are the functional requirements. Let's see what are the non-functional requirements. The cache should be highly available. What is meant by highly available? It should be able to work in case of network or network partition or power cuts. So if the network goes down or if there is power cut, it should still be able to work. Okay, it should still be able to serve all the functional requirements. That is one thing. Then next thing is high throughput. We already discussed that cache memory is really fast, so it needs to read and write data very fast. So that is why we need high throughput. And since it is a distributed system, it should be scalable. It should be, whenever the data storage requirement increases, our caching service should also be able to scale accordingly. So these are the non-functional requirements of our caching service. Now let's try to build a high level design of the system. Okay, the very first thing that we will address is we'll need to split the data onto multiple servers. Why? A single cache server won't be able to accommodate this data. Okay, now since we are talking about distributed application, we'll have multiple application servers as well. Okay, so we have two choices for caching servers. We can use the application servers itself for caching also, and we can have a separate caching layer which will have multiple caching servers. So if we utilize application servers for caching also, it is known as co-located caching. If we have separate caching servers, it is called as dedicated caching. Let's try to understand the advantages and disadvantages of these. Let's begin with co-located caching. So in co-located caching, if you try to scale one thing or one service, let's say application service, the caching service would get scaled automatically. So scaling app and cache goes hand in hand. Next, the capital and operational expenditure would be reduced. Why? You are not using separate cache servers, so you don't need to buy separate cache servers. So you save your investment on having separate cache servers. So also, since the app and cache is present on same servers, to some extent you also reduce the operational expenditure. So you save capital and operational expenditure. But since the app and cache are present on same server, if the server fails, both the services would fail. The application would also fail and the caching service would also fail. Okay? Now let's discuss the pros and cons of dedicated caching service. Now since both the services are decoupled, you have choice here to use separate hardwares for your application and for your caching. Okay? That is one advantage. Next is, both of them can be scaled independently. At times you may have requirement just to scale caching layer, or you may have requirement to scale the application layer. So since both the services are decoupled, you can do that independently. So if you have a separate caching service, other microservices can also use this caching layer. So these are the advantages of dedicated caching service. Uh, we assume dedicated caching service for our further discussion in this video. Okay? We have already established that we'll need to split our data onto multiple servers, right? But it introduces certain problems. What are those problems? The very first problem is that how will we ensure uniform distribution of data onto all partitions? This is one problem. Next is how will our app servers know which partition to put data on and which partition to get data from? That is another problem. You may suggest that hashing is a solution to this thing. Okay? It is solution, but hashing itself introduces other problems. So let's say initially when you hashed things, there were n servers and caching servers. Okay, so all the data is hashed onto n servers. But let's say now if a server goes down or a new server is added, as n+1 is added, all the data that was hashed onto this particular servers, it's not valid now. If the number of server reduces to as n-1, the data needs to be redistributed onto as n-1 servers. So the hashing that was done earlier is invalid now. This is another problem. What is the solution to this problem? It is consistent hashing. Whenever you partition data onto multiple servers, in order to deal with these problems, you introduce consistent hashing. I have already created a detailed video on consistent hashing and I'll put the link of the video in the description. You can check it out there. Okay? So consistent hashing would solve these problems. But where would this consistent hashing run? So on each app server we'll have a cache client library that will do the consistent hashing computation. So on each app server which will have a small library which is cache client, and it will do the consistent hashing computation, which will map which data is supposed to be present on which caching server. Okay? So how does our high level design look like? We have multiple clients. These clients will get onto our caching service through load balancer or API gateway. Okay? The very first layer we have is the application servers, and we have already established that our application servers will have a small client library that will do the consistent hashing. Okay? So each application server will have this cache client library. This cache client library will do the mapping of which data is present on which cache server. Each cache server is going to have the hash map and the doubly linked list that will implement the caching service on each cache server. Now the consistent hashing will tell each application server where to fetch the data from and where to put data onto. Okay? And post that we have the database. If some data is not found in the cache, it will fetch the data from the database. So this is how our high level design looks like. Now while designing cache, there are multiple policies you will have to consider. The very first policy is writing policy. What does writing policy do? Writing policy decides where will the data be updated first. Is it going to be the database, and is it going to be the cache? Okay? Now based on different writing policies, you get different kinds of consistency. If you choose write through cache, you get strong consistency between the data present in database and cache, whereas if you choose write back policy, you get weak consistency. I have discussed these policies in detail in my caching video. The link is present in the description. You can go watch that video. Next is the eviction policy. What does eviction policies do? Eviction policies decide when the cache is filled, which entry in the cache would be kicked out. Okay? Based on use cases, you can have multiple eviction policies: least recently used, least frequently used, most recently used, FIFO, etc. So there are multiple eviction policies that you can choose to decide based on your use case. Okay. Then there are cache invalidation policies. So uh, based on what eviction policies we have used, there could be some data that does not get evicted out of the cache. This data after some time becomes stale and is invalid. It needs to be updated, but that cache entry has not been updated. That particular entry in the cache, it has not been chosen to be updated, or the data present in that particular entry has not been kicked out. So such kind of entries needs to be moved out of the cache. How do we do that? It is done using time to live variable in the cache. So for each entry in the cache, we maintain a time to live variable. For each entry in the cache, we maintain a separate time to live variable. When this time to live variable expires, we'll move out the particular entry in the cache. This cache entry becomes empty. So this is called as cache invalidation policy. Okay, now we have discussed the high level design of cache. Let's deep dive into it and let's see what all problems can this high level design have. Very first thing is that all the cache client need to maintain same list of cache servers for consistent hashing. We discussed that all the cache clients will do the consistent hashing, right? But they need to maintain exactly same list of cache servers. Why? Why do they need the exactly same list of cache servers? If cache clients have different list of cache servers, two different cache clients may end up putting or getting data for the same data request, same data item onto different cache servers. This will lead to a lot of cache misses. So let's consider there are two cache clients and they have different list of cache servers. Now they do consistent hashing and both of them will have different mapping of data to cache server. So one cache client may end up putting data on, let's say, server X, and other client may try to read the same data item from server Y. This happens when our cache clients have different list of cache servers. So it is important that all the cache clients receive same list of cache servers. Okay. How do we solve this problem? We solve this problem by introducing a coordinating service. Okay? A coordination service. Now what does this coordination service do? Very first thing it does is that it keeps checking for heartbeats from cache servers at regular intervals. Okay? So it keeps checking for these heartbeat signals from cache servers. Next, it maintains the list of all healthy servers onto itself. And at regular intervals, it will share the list of all healthy servers with all cache clients. That is how all cache clients can have the same list of healthy servers. But if this coordination service runs on single machine and if the coordination service fails, it will lead to single point of failure. The cache clients will now not have the list of healthy servers. It will try to put on data onto some unhealthy server as well. Okay? So that is a problem. What do we do for that? We don't run coordination service on single machine, we'll run it on multiple machines. Now out of that, one of the coordination service will be active service and others will be passive. Okay? They also keep sending heartbeats to each other so that they know that the active service is live and the passive services are also live. Now when this active coordination service goes down, the leader election algorithm like Paxos or Raft will kick in. For leader election algorithms, we can also use Zookeeper. So this leader election algorithm selects one of the live passive coordination service and that leader will assume the responsibilities of active coordination service. Now you may ask that what will happen to the list that is maintained by these services, list of healthy servers. We'll maintain the list of healthy servers onto a separate database. So when the active coordination service fails, the list of healthy servers is not lost. It is not lost. So that is how we ensure that the list of healthy servers remains intact, and the passive service that assumes responsibilities of leader, it will also have access to the same list of healthy servers. Now let's discuss how do we ensure availability. We have partitioned our cache into multiple servers. Okay, now if one server goes down, all the data that is cached onto that particular partition will be lost. It will lead to lot of cache misses for all the requests that hit that partition, right? How do we solve this problem? We will maintain synchronous replicas. Okay, now what are synchronous replicas? Synchronous replicas are the replicas which will have to maintain communication with the leader cache server. So they will have to send back acknowledgement onto the leader cache server that whatever write request they had received, they have returned that particular request. Let's see the order of write request on to between the leader and the synchronous replicas. Whenever the cache server receives a write request, it propagates that write request onto the synchronous replicas. Okay. Once the synchronous replicas send back the acknowledgement, then the cache server would send the acknowledgement back to the client that we have written this data. Now why are we maintaining synchronous replicas? Why are we not maintaining asynchronous replicas? It is because we want to avoid inconsistencies. Let's say if the leader goes down and we have maintained asynchronous replicas, then there is a possibility that the data present on asynchronous replicas is inconsistent. Okay, because there is no communication between synchronous and asynchronous replicas, so there is no acknowledgement coming back from asynchronous replicas to the leader that we have written the data that you have sent. That is why we maintain synchronous replicas to avoid inconsistencies. Now we also keep these replicas in proximity with each other because we want to avoid communication delays. We know that caching needs high throughput and we need to avoid every possibility of latency. That is why we keep them in close proximity. Now there is one more problem. Let's consider example of Virat Kohli's Instagram profile. Virat Kohli's Instagram profile is present on one of these cache servers. Okay. Now if many users try to access Virat Kohli's Instagram profile, that particular cache server will receive a lot of requests, right? As a result of this, the cache server is overburdened, and it will give back slow response. So whenever there are read requests, these read requests can be sent to the synchronous replicas. So the synchronous replicas can serve this read request very well. So replication also helps solving the problem of hot sharding. The shard on which Virat Kohli's profile is present is hot shard because it is receiving lot of requests. These requests can be served by asynchronous replicas. So replications help solve the hot sharding problem. I hope you would have understood this. Thank you.